Kundu.
Yes, sir. Good evening, everyone. Myself Bendu Kundu from
I
West
think
Bengal, Kolkata.
you are a Bengali guy, na?
Yes, sir. Yes, sir. I'm from
Okay,
West
okay,
Bengal,
okay,
Kolkata, and I'm a
okay,
master's in chemistry. And presently, I'm working with Mitsubishi Chemicals, that is in Holdia, as a senior chemist.
okay,
That's all.
okay. Very good. Then it is followed by Josephine.
Sorry.
Okay. Then no, you are over. The Dibyendu, you can mute now. Ria Bhargava.
Good evening, everyone. My name is Riya Bhargav. I'm from Aligarh, Uttar Pradesh. I did my graduation in life sciences from Delhi University, and nowadays I'm working as a medical writer in a US based company.
Very good. Thank you. Sumitra Pradhan.
Yes, sir. Good evening, sir.
Good evening.
Sir, my name is Sumitra Pradhan. I'm from Cuttack and I completed my graduation in Banki Autonomous College,
Mhm. In which subject?
chemistry.
Oh, okay. We have left with two, that is Swarnamai Pradhan. Is she here? Okay. So anyone who which I left, you may give an introduction, then we may proceed. So today we will discuss your second paper, that is MCH-002 paper. Just wait, I am sharing my screen. I think my screen is shared now. So anyone, please reply.
Yes, sir. It is. Yeah.
This the PPT is visible.
Yes,
Yeah.
sir. Yes, sir.
Okay, okay, okay. So in the second paper, your topic is related to separation techniques. So why the separation techniques are required in chemistry? Because we are surrounded by numerous complex materials. It may be organic, inorganic, or both type. So this techniques, separation technique is required to have or to have uh, a pure substance recovered, and this pure substance may be used for different chemical analysis. And so this particular branch of science is also known as separation science, that involve different separation techniques, or this is a way to separate mixtures particularly. So if I go for the textbook definition, then separation is a process by which a mainly mixture, it is minimum of two components or more than two. So which is a mixture which is divided in at least two components with different compositions, or two types of molecule with the same composition but different stoichiometry or stereochemistry. So the ratio may be different, or the stereochemistry may be different. So the stereochemistry related to your, that is the different type of configuration. It may be R, it may be S, or it may have a chiral carbon center if it is an organic compound. So it is also applicable to inorganic mixtures. So by different separation techniques, we can able to separate at least two components in a mixture. So separation technique touches every branch of science and technology, because by separating the components, we are able to purify the samples and accordingly we can use in our chemical analysis. So separation technique also have developed into a well-established branch known as separation science. So these separation techniques, the applications are in the field of biological sciences such as biochemistry, biotechnology, clinical pharmacology, therapeutics, and toxicology. The progress has taken place prominently because of the advancement in the separation methods. So this is very much clear. After going through the proceeding text, you would realize that separation method form an important component of chemistry, particularly analytical chemistry, because in analytical chemistry we are using different types of analytical methods that is mainly related to spectroscopic methods or your chromatographic methods. So for spectroscopic method and chromatography method, we must require a pure sample which we have by different separation techniques from a mixture. So in analytical chemistry, what happened? There is interaction between your material and EMR, that is electromagnetic radiations. So electromagnetic radiations, what is known as electromagnetic radiation? The radiations which are associated with both electrical and magnetical field. It is known as electromagnetic radiation. So just wait. Okay. So the interaction between material and electromagnetic radiation is known. It is the basic principle of your analytical chemistry. So electromagnetic radiation, it involves your cosmic ray, X-ray, gamma ray, UV visible light, IR light, infrared, then radio wave, microwave. These are all your electromagnetic radiations. And electromagnetic radiations always it travels in a straight line, and it has almost no effect of your vacuum. So these things we will discuss in later part. So this is mainly needed for our different biological processes as well as in our basic chemistry as well as in the analytical chemistry. And in this category there is a very important part that is in separation technique, which is your chromatography method. So we will have different units on your chromatographic methods. So what are the objective of this unit? That is unit 1. So the objectives are to appreciate the separation method as a unified science, describe the scope and utility of separation methods, discuss the evolution of chromatography, explain the classification of separation methods, and we will able to list the criteria for the selection of separation methods. So these are the primary objectives of our separation technique of this unit. That is, these methods, just wait. So these are the objectives we have in this unit. That is, what are the scope, utility, and how the evolution of chromatography will be there, and different classification of separation methods. Then it is followed by different criterias. Then if we go for the classification of a mixture or of a separation technique, it is based on different property of the mixture. That properties maybe the volatility followed by solubility, partition, ion exchange, surface activity, molecular geometry, or electromigration. So one by one we will discuss. So in general sense, the volatility is related to your the escaping tendency. The escaping tendency of a component from a mixture is known as its volatility, and it is very much related to your vapor pressure. So if the escaping tendency is more, then vapor pressure will be more and the volatility property will be more. That means how easily or how at a room temperature or at ordinary condition, how a component is separated from a mixture based on their volatility property. This is depends on their escaping tendency. Like our alcohol or acetone or phenol, you may say. So these things, if I open the lid of the bottle, then after some time the volume of the alcohol, the volume of the acetone, or the volume of the phenol will reduce. Why? Because at ordinary temperature these chemical have higher escaping tendency or higher vapor pressure. That's why um, they change from liquid to gaseous state. So that's why they will separate. It is followed by your solubility. So how in a particular solvent a component is soluble. So that is another property. So by which we can separate different component of different components in a mixture. Then the third one is partition. This partition is based on your chromatography. It is based on your chromatography. So in chromatography, what happened? In the basic sciences, in chromatography, there are two phases. One is mobile phase and another is stationary phase. So we run the mixture on that solid phase, that is the stationary phase, and a liquid phase is run above the solid phase or stationary phase. Then what happened? On the basis of the partition coefficient, on the basis of the partition coefficient, the different components of that mixture will be stick on the chromatogram, and from that process we may separate different components in a mixture. So that is based on the partition. That is the ultimately this is the chromatography. Then ion exchange chromatography will be there. Ion exchange, when ion exchange happen, and this method is only applicable when the components are ionic compounds. So if the component is ionic compound, then different ions will be formed or different ions will be generated, generally the positive ion and negative ion, that is for cation and anions, and the cation and anions will be detected by the chromatography, which is known as ion exchange chromatography, or this is another property of the component in a mixture by which we can separate. Then surface activity, this is based on the surface property, that is on a particular membrane or a particular surface, how different components of a mixture is forming bonds or is attached to the surface. This is another property. Then it is followed by molecular geometry. This is also an important property, because based on the different molecular geometries of a component, of different components in a mixture, they can be separated accordingly. So molecular geometry is very an important property. Then electromigration is there. Electromigration is what happens. This is just a version of your Faraday's first law, that is electrolysis method. So by which electroplating, separation of copper or zinc, or separation of silver from silver nitrate, these things are there. So the application or the property is known as electromigration, where different ions are migrated to their respective electrodes. That is, positive ion will migrate towards anode and negative ions will migrate towards cathode. in galvanic cell. So in that way we can separate different ionic components or ionic compounds by electromigration method. So out of these 7 properties, the property of ion exchange and the property of electromigration, these two property are generally based on the formation of different ions from the components in a mixture. So from which type of compound the ions will be formed, that is the answer will be the ionic compound. If the component is of an ionic type, then the um, methods which are based on ionic exchange or electromigration may be applied. Then we have the classification based on equilibrium. We will have mainly of 4 equilibriums, that is gas and liquid, gas to solid, liquid to liquid, and liquid to solid. Generally these 4 type of equilibriums are there or are seen in a mixture or in different components present in a mixture for separation. So these things we will discuss later. Then we will classification based on rate processes. So I just read out the things. The separation based on rate processes take place due to difference in the kinetic property of the component of the mixture. So this rate is related to the kinetic property. That is how fast a component is moved from the mixture to their respective points. It is known as the rate process. The separation are mainly achieved due to the 2 regions: the different diffusion rates through permeable barriers such as membranes, or different migration velocities under various fields like electrical, gravitational, or thermal. So the first one, that is the application of a permeable barrier, that is a membrane. If I go for an ordinary example, if I go for a water purifier, let us it be AquaGuard, Kent, or something else. In a water purifier, what happen? These membrane application will be there, and the chemical technique or the separation technique used in water purifier is known as RO, that is reverse osmosis. So in reverse osmosis, what happen? There is application of semi-permeable membrane. So what is the role of a semi-permeable membrane in water purifier? This semi-permeable membrane will allow only the solvent particles, because ordinary water is a mixture. It is a mixture of water, that is total dissolved solid will be there, some soluble and insoluble salts will be there, some impurities will be there. So ordinary water is a mixture. So how the pure water is, the component pure water is separated from a ordinary water, from an ordinary water? How it is possible? It is possible through by using a membrane, and that membrane is the semi permeable membrane. So the semi-permeable membrane, you can say an example, that is the outer layer of an egg. If I go for a boiled egg, अगर हम क्या करेंगे, एक बॉइल्ड एग को लेंगे और उसका जो ऊपर वाला जो रहता है उसको अगर छीलेंगे तो क्या होगा ना, उसके अंदर देखेंगे एक वेरी सेमी पर थिन लेयर ऑफ एक कोटिंग इज देयर, which is same as a semi permeable membrane, and that membrane is only allowing the solvent particles and not allowing the solute particles to pass through it. So this will allow only the solvent particle. So that type of membrane is used in water purifiers, which allow only the water to pass through it, and by separating all the impurities or insoluble salts present in ordinary water. So the second reason is, it is the migration velocities under different fields. and this is just same as our the electromigration. If I go for the electrical property, then it will be electromigration. That is, different ions will migrate to their respective electrodes or respective points on the basis of their charges. If I go for a anion, it will migrate towards cathode, and if I go for an cation, it will migrate towards anode. This is general principle, and the rate at which the rate at which these ions will migrate depends on their kinetic property. That depends on their size, their charge. If the size is small or charge is high, then their migration will be high. So this type of factors will be there. So students, up to this, it is okay, or anything else you wish to ask or share? Am I understandable, or am I go fast? Anyone?
Yes, sir.
Iqbal, is it okay, or am
Yes,
I
sir.
going?
Okay, sir. Okay.
Okay,
No,
okay,
sir.
It is okay.
okay, okay, okay. Thank you. So please mute. Please mute. Then what are the different type of methods of separating mixtures? The methods in a separating mixture, that is separation methods in a separating mixture. This is the number one is your magnet. So by using a magnet, we can separate the magnetic components. So what are the magnetic components? These are generally ferromagnetic, ferrimagnetic, pyromagnetic. This type of magnetic substances will be there, which we can separate these things by using a magnet, except the anti-magnetic substances. Then the simplest one is the filter, which we generally use in our chemistry lab or any research lab. This is a common procedure to separate the filtrate from the residue, or separation by filtration. So for this, a funnel will be required, filter paper will be there required, filtration stand will be required, these things will be there. Then decantation is a process. Just by decanting the upper liquid or upper we can say liquid, yes, the upper liquid layer from the solid. Then evaporation will be there. Evaporation is by the application of heat. The liquid or the solution or the solvent will be changed to this gaseous form, and this will be separated on the basis of their escaping tendency. Again, the escaping tendency will be there. The less heat, if the component is evaporated, that means it has a higher escaping tendency. If more heat is required, that means escaping tendency is less. If escaping tendency will be less, volatility will be also less. Next will centrifuge. This is a centrifuge instrument is there. So where centrifuge will be happening, and we will separate the components. Then chromatography, I already told to you. In chromatography, different components are separated on the basis of their partition, or that is known as partition coefficient. Then the last one is your distillation. Distillation is mainly the water distillation, that is to get the distilled water from ordinary water. So this is a process of your filtration, where a mixture of solid liquid are there in this beaker, and we are using the funnel. Then another beaker is here, and we have used a filter paper here. By using the glass rod, that is the staring rod, glass rod, we may filter the mixture, and we may separate the things. That is, this is the filtrate part, and this will be the residue part. And this is the distillation process, traditional distillation. And in many chemistry lab or research lab, you may see this type of distillation units. So that it is distillation processes by giving heat or by supplying heat. This ordinary water will be, the water will be evaporated, converted into steam, and by using this condenser, that is a cooling chamber, the steam will be cooled, and this is again changed to the liquid water. So by this process we are able to collect pure water, or that is distilled water. So under method of mixture separation, we have the number one is a mechanical separation, that is separation by hand. So this is just a physical separation type. So by which we are able to separate different solid samples, mainly the solid samples. That is, example is your recycling, plastic, paper, metals, etc. This can be separated based on their color, shape, like properties. Then this is example of your magnetic separation. So by magnetic separation, this is an example, that is, this is iron plus sulfur. If I apply or use a magnet, then the magnetic substances, whether ferromagnetic or ferromagnetic type substances or components, will be separated, and we will have separation here. So this is separating metal in a scrap yard. And this is generally the filtration type, where funnel, beaker, filter paper is used. Then in filtration, takes advantage of the physical property of the state of the matter. A screen lets the liquid particle through but trap the solid particles. So this filter paper will trap the solid particle, which is also known as the residue, and it is allowing the liquid part to pass through it. So filtration is dependent on the state of the matter. So liquid state will be passed and solid state will remain here. So these are the solid parts, and these are the liquid, that is filter paper has many minute pores are there, which allow the liquid part to separate. This is a decantation process, where the upper liquid layer is decanted off, that is to pour off the liquid, leaving another liquid or solid behind. So takes advantage of difference in density. So for two liquids, the property of density is a matter of concern. So where the density is more, this will be at the bottom level, and the density is less, it will be at the upper level. So upper level liquid will be decanted off like this. So this is a chromatography, your application. So this is dye t-shirt, black pen, ink. So these are the example of your chromatography application. Then chromatography is an important technique in separation science, because this is very much useful in science labs, that is your research labs. So for many chemistry or biomedical or biochemistry, biotechnology labs, these separation techniques is frequently used to know how the reaction is completed or not, how this component is present or not. So these things you can easily trace by using the chromatography method. So a short history of this chromatography is, the principle and the application were reported in 1906 by Russian botanist Mikhail Sweat. So he is Mikhail Sweat, who was reported the first principle and application of chromatography, and he described the resolution of chlorophyll and other plants pigments in plant extract. So the first attempt to chromatography is the resolution of chlorophyll and different plant pigments. And later, this chromatography method, that is a separation method, was advanced by James and Martin. So he is James and he is Martin. The impact of chromatography has been very great on all the areas of analysis and on the general process of science. So they both rewarded or awarded two Nobel Prize in 1952 due to their advancement in chromatography. That is James and Martin. And this is just an example of your paper chromatography. So this is also known as thin layer chromatography. So this is under your paper chromatography. So where a paper is used, that is a this paper, it is a chromatograph paper. So this is a very unique paper, and this is this paper. By using this paper, we can separate the different components of a mixture. So how? So different parts of this paper chromatography are, this chamber is known as chromatogram or chromatography chamber. This bottle, this is known as chromatography chamber or chromatogram, and this paper is known as chromatography paper or paper. Okay, or thin layer chromatography, this is also known as. And at the bottom there is a solvent here. The solvent may be hexane, and this is of different ratios, that is 1 is to 1, 1 is to 2, or 10%, 50%, 20%, depending on the partition coefficients. This solvent is used. Okay, so so in paper chromatography, what happened? So you will have to put, just see here, you have to put one line here first. So you have to mark the three spots, that is 1, 2 and 3. So in first one, if I go for a chemical reaction, that is the two reactants will react at a particular condition to give the product. So how we can estimate or determine the reaction is completed or not, or how much the reaction is undergoing, what percentage of the reaction is completed. So these things we will determine through by using this paper chromatography. So in these 3 points or three marked points, let us, in the first one I have put the reactant 1 and 2 I put here, and the second one I have put the reaction mixture, right? This is the reaction mixture. So this is the reactant, this is the reaction mixture, and this is the final product I have put here. So this is reactant, reaction mixture, final product. So by using the capillary tube, very minute thin tube, which we use here, that is a capillary tube. Just put the first one, the reactant, second one the reaction mixture, third one is the product. Then after putting this paper in the chromatogram of, let us 10% hexane. 10% means it is 10% 10 milliliter hexane and 90 milliliter water. Okay, so 10 ml hexane and 90 ml water. So it is used as the solvent. So by putting this 10% hexane, I put this paper inside this bottle, and I will close the lid or close the mouth. What happened? After some time or after few seconds, I will see this type of things. The see, I will see this type of thing. Gradually the spots will float upper, because the points will the spots will be flow upward, because due to this solvent, this paper will become wet, and gradually the solvent will move up. If the solvent will move up, it will react with these spots, and on the basis of their partition coefficient, this will go up. So the different spots will be there, and these spots will be seen under ordinary light or under ultraviolet light. So after this, we will match where the points are. So if this is the reactant, then this is reactant 1 and reactant 2, and in our reaction mixture or product, the reactant 2 is there. So that means the product, this reaction is not completed. The reactant is present here. So like this, by comparing the spot level in three different zones, we will able to detect how the reaction is completed or not, how much reactant is left out, or what is the condition of the reaction, by comparing the level of the different spots in three different zones in the paper chromatography. So these things we will discuss in our next unit. Then the this is known as the liquid chromatography, that is LC, liquid chromatography, or this is the general principle of chromatography, where a stationary phase is here. Okay, so this is the stationary phase. Generally the stationary phase is your solid phase or solid state. The solid state is known as the stationary phase, and this is the mobile phase, and the mobile phase is generally the liquid state. Okay, so this is the solid phase, this is the stationary phase, and this is the mobile phase. So this is a mixture, sample mixture. So what happened, just see, if I pour the sample inside the chromatogram, so the total system is known as chromatogram. Okay, so if I go for or if I pour the mixture inside the chromatogram, then it will react, or it will attach to the mobile phase on the basis of their partition coefficient. Then gradually this mixture will float, and gradually the different components will separate on the basis of the different reaction capacity or their attachment to the mobile surface. So, and at last, with the help of the detector, we can detect different components in the mixture. So the component which is less adhere or less attached to the mobile phase will be separated first. The component which is more attached or more reacted to the surface or to the mobile phase will be separated last. Someone is unmuted. Who is he or she? Is Rishank? Please mute yourself. Yes. So the component which is less attached to the mobile phase will be separated first, and the component which is more attached or reacted to the mobile phase will be separated last. So this is the principle of your chromatography, that is liquid chromatography. And the first one is your paper chromatography. Okay. So just see, this is the detector, this is the sample, this is the solid phase, mobile phase. Then what happened? Just see here, mobile phase. Then I put the sample here, and gradually the sample migrate, and the different components are separated. Then at last we are able to separate the components individually on the basis of their partition coefficient. And this is ion chromatogram of orange juice. So in orange juice, if I go for the detector response and time in minute, we have different ions present, and this will be based on their different ions migration, that is rate process. So after 5 minutes I have Na plus ion, after 10 minutes we have K plus ion, and these things will be there, that is with respect to time. This is setup to heat a solution. So this is a general setup. You all knew it. That is a Bunsen burner will be there, wire gauge will be there, beaker will be there with some solution or mixture. Then this heat process is also an effective method for your separation technique. Then a distillation plant. So different components or different parts in a distillation apparatus are, this is the round bottom flask, it is attached to a thermometer, and this is just the distillation stand. Bunsen burner is there. This is an additional tube is there which is connected to the condenser, and this is the conical flask receiving the distilled water, and we will have the cooling chamber which is always connected to the tap water. Okay, so these things are there. So this is the cooling chamber, this is the hot zone. The solution is boiled and steam is driven off. So this is the ordinary water, and that is the salt water. Ordinary water which is contained the salt, that is salt water. If the waters are evaporated, then the salt is only left out. Just see here, only salt is left, and this is the pure water here. So no chemical change occur when salt water is distilled. So no chemical reaction is supposed to be happening, and a salt water solution a homogeneous mixture. So in a homogeneous mixture, the salt and pure water is separated by simple distillation method. Then we have sand salt water mixture. So sand salt water means for the first step will be the filtration step. So in filtration step, the sand is separated and the salt water gets separated, and this salt water solution will be distilled to give salt and water. So three components are separated by using two separation techniques or two separation methods. The first one is filtration, and the second one is your distillation. So this is again theoretically, that is salt crushed with sand. Then how we can exactly or chemical the experiment can be carried out in exact manner. How we can perform the calculation part, that is salt crushed sand. We have to wet the mixture, pour the heat resistance, fill with water, stir for 1 minute, and these things will be there. Okay. So this is also very important. So under distillation, we have mainly 5 types of distillations are there. Mainly 5 types of distillations are there. The number one will be fractional distillation. Number two will be flash distillation, vacuum distillation, steam distillation, and azeotropic distillation. So under fractional distillation, it involves the return of condensate to the distillation unit under conditions such that this condensate is continuously and counter currently in contact with the vapor. By this method, you can achieve greater enrichment of vapors of more volatile components than that obtained by simple distillation. So fractional distillation means it is distillation fractionally, so by phase wise. So then this is followed by flash distillation. So there is an instantaneous and continuous vaporization of a definite component of the mixture such that the total vapor produced is in equilibrium with remaining liquids. It is followed by vacuum distillation, where vacuum is produced. It is actually distillation under reduced pressure. It is used to separate high boiling mixture or liquids that decompose below their normal boiling point, or low pressure reduces the boiling point. So this is your under pressure. Then it is followed by steam distillation. So it is employed to separate a component from a non-volatile impurity. The boiling temperature of the mixture is reduced by vaporizing it in a stream of carrier vapor, say steam, which upon condensation is immiscible with the original mixture. A separation can be readily achieved. And the last one is azeotropic mixture, where the same boiling temperature components gets mixed, and this azeotropic distillation is used to separate this kind of mixture. So azeotropic distillation is used for separating components of a mixture which have a boiling point very close to each other. The relative volatility of the component of the mixture is altered by adding another substance. This description will give you an idea about the different ways of distillation, that is five types, that is fractional, flash, vacuum, steam, and azeotrope. Then this is another method, that is the centrifuge method, where a centrifuge chamber is there. Generally, the separation of a blood or a DNA from blood, this type of medical applications are there. So by using this centrifuge method, we can separate different components in a blood or DNA from blood. This is centrifuge chamber here is here. We can use A, B, C, that is three types of samples are here, and this is blood, then the RBC, red blood cell, serum gets separated, and this is just an application of your centrifugation. This is spin, sample very rapidly, denser materials go to bottom, separate blood into serum and plasma. This is very simple method, that is based on the again the property of density. So where in which the density is more, the component in which the density is more, it will be go at the bottom, and the density is less, it will go up. This is very common phenomenon. And the application is the detection of anemia, that is lack of iron. This is just the water molecule. We that is two hydrogens and one oxygen is here. So water molecule, the different component, that is the H plus ion and O2 minus ion, is separated by using the method of electromigration. So just see here the decomposition of water molecules. That is, this is the water molecule. If we apply the electric current, then the oxygen and water O2 and H2 gas will get separated. But this is the theoretical equation. But in practically what happened, this is the electromigration apparatus, where we have the ordinary water here or the distilled water here, and the component, that is hydrogen gas and oxygen gas, will be separated based on their charges. And in the on the left hand side, oxygen gas is formed, and on the right hand side, hydrogen gas is formed. And then two electrodes will be there, which may be made up of platinum or carbon, because these two electrodes are neutral electrodes. Just see here, this is the diatomic oxygen and this is diatomic hydrogen molecule. This is the electrolysis process. Electrolysis means, this is electro means electricity, lysis means to separate. And here the water in presence of acid, H plus ion, will separate like this, and this is the half cell reaction, that is cathodic reaction, that is reduction, and anodic reaction, that is oxidation. And here in the cathodic reaction, reduction will supposed to happen. Here what happened, the H plus ion, that is in water, H2O, the H is present as H plus, O is present as 2 minus. So H plus is converted to H0. That means reduction is supposed to happening here. So if reduction is happen, then the electrode is said to be cathode. Now, this is the cathodic reaction, where hydrogen gas is liberated with OH minus ion, and in the anodic end, oxidation reaction is happen, and here oxygen gas is liberated with the evolution of S plus and 4 electron minus. So here addition of electron is there, that means it is reduction. It is removal or loss of electron is there. It is oxidation. So by any definition, you can distinguish where is reduction and where oxidation is supposed to happen. So if I go for the basic definition of oxidation reduction, then oxidation in which oxygen is added or hydrogen is liberated, or we may say oxidation is a process in which oxidation number increases or electron is lost, that is loss of electron, that is known as oxidation. The reverse is your reduction. Then criteria for select. So how we from these numerous methods, a number of methods or different methods, how we can select the method which is suitable to our sample or our mixture, whether I am going for physical method, filtration method, chromatography method, or electromigration or ion exchange, or your electrolysis method. So these methods are there. So how we can select, sorry, how we can select the different methods for a given mixture. So we can thoroughly study the selectivity level, the detectability, the yield, speed and convenience, the capability for hyphenation, and ease in scaling up and economics. So these things will be there. So uh, by reviewing all the conditions of your surrounding, that is in your lab or any scientific area, and depending upon your availability and depending upon your yield, that is the productivity, and the speed at which you are expecting your result, and the convenience, how convenient it would be, how the detectability, how we can easily detect the different components, how selectively we can separate. So these things will be there. And at last, the final aim of every work is to save money. That is the economics part. If I separate 100 rupees component, and I spent 1000 rupees for separation taking technique, so this will be no meaning. So I should have, or we should have, the sense of economics, that is we should expend less money. Okay, so this is all about your unit 1. And after 5 minutes we will go to the second unit. This is, I think, we'll go to the second unit, that is your solvent extraction part 1. So unit 1, we have discussed the general sense of your separation technique, and this is becomes your core 1, that is the solvent extraction 1. So after 5 minutes we will again come back. Thank you.
प्रकाश सर नमस्कार. Dear learner, sir will join or what? Am I audible
Sir
to all
said
of
sir
you?
will join after 5 minutes.
Am I audible to all of you?
Yes, sir.
Sir, what sir has finished the class or sir will join?
No sir, class will be continued after 5 minutes, sir.
What,
First
what,
chapter is
what?
finished, so second chapter will start after 5 minutes, sir said.
After 5 minutes he will start. What he told? Sir will join again though.
He will continue
Yes, sir.
class after 5 minutes.
Okay, fine. Okay, fine. Thank you. Okay, fine.
Welcome back, students. Unit 1, we will go to our next unit, that is Unit 2. So, am I audible to all of you?
Yes, sir.
Okay. So, now I am sharing my screen. Yes. Is it visible, the PDF? Solvent extraction 1. Is it visible?
Yes, sir.
Okay. Okay, thank you. So, in Unit 2, we will be specific now. That is, we will discuss different separation techniques one by one, briefly. So, in this part, that is solvent extraction 1 part, we have the general terminologies and different type of principles involved in the different solvent extraction processes. So the principle involved is your phase rule consideration. That is, phase rule means it is just your Gibbs phase rule, which is very much learnt by our chemistry student. That is, phase equilibrium is there, and Gibbs phase rule will be there. That is F equal to C minus P plus 2, where F is degree of freedom, C is number of components, P is phases, and this is minus 2 will be there. Then it is followed by distribution law and its limitation. So what is distribution law? That is, if a particular solute is distributed in two different solvents, That is, let us, one solute is dissolved in water, at the same time it is dissolved in organic solvent, that is aqueous solvent and organic solvent. So how this distribution will help us to separate the components? It is based on distribution law, which is proposed by Nernst. Okay, so this is also known as a Nernst distribution law. Nernst is a scientist name. Then distribution ratio is, what is distribution ratio? It is nothing but the solute present in the organic phase divided by solute present in the aqueous phase. This is known as distribution ratio. Then percentage of extraction, so how percentage, or what percent, so not how, it is what. So what percentage of the component is extracted from a mixture in percentage, that is out of 100, it is known as percentage extraction. Then what are the factors are there? Separation factors are there, multiple extraction processes, then classification of extraction systems are there, which is mainly based on some different type of distributions, then it is your extraction by compound formation, which is followed by extraction by solvation, ion pair formation, crown ethers are there, that is host guest molecule are there, crown ethers. It is followed by diluent and modifiers, etc. Then we have summaries are here. Then in extraction process, the main objective of this unit is to explain general principle and terminology used to express partitioning of solute and efficiency of separation, classify extract used for metal ions, and the role of diluent or modifiers in the extraction of metal ions. So these are the basic objectives of this unit. So the first we will go for the general principle and terminology. The first principle is your phase rule, which is given by the Gibbs phase rule. That is F equal to C minus P plus 2, or in other mode it is also P plus B equal to C plus 2. That means where P is the number of phases. Phases means in general terminology we can say it is the states. If I go for water, then water has 3 states. That is, in solid it is ice, in liquid it is water, and it is gas, it is water vapors. So for water, P equal to 3 number of phases. Then V is the variance or degrees of freedom. So this will be calculated. Okay, so number of degrees of freedom depending upon different conditions. C is the component. Our component is 1, that is only water. So that means for water, C is 1 and this is plus 2. So if I modify this equation and if I replace the symbol B by F, it will be F equal to C minus P plus 2. Just do here. If I go for V equal to C minus P plus 2. That means for water P equal to 3, for water C equal to 1, and we have to calculate the V or the degree of freedom, that is F. Then distribution law and its limitation. So it was first enunciated in 1872 by Berthelot and Jungfleisch, and later elaborated by Nernst in 1891. And what is the textbook definition? This law states that a solute will distribute itself between two immiscible solvents. That is, immiscible solvents mean it is organic and inorganic solvent. Or we may go for polar and non-polar solvent. If I go for a polar solvent, it may be an inorganic solvent. If I go for a non-polar solvent, it may be an organic solvent. So that the solvents will be immiscible in such a manner that at equilibrium, the ratio of the concentration of the solute in two phases at a particular condition of temperature will be a constant, provided the solute has the same molecular weight in each of the phases. This is very important. The solute has a same molecular weight in each of the phases. That means in aqueous phase as well as in organic phase, that the solute will be distributed almost equally in the two phases, that is solid phase and that is organic phase and aqueous phase. So for example, if I go for a solid S which is dissolved in or distributed in two solvents 1 and 2, then I can write at equilibrium the solute in solvent 1 will be at equilibrium with the solute in solvent 2, that is S2. S1 is equilibrium with S2. That means if I go for the equilibrium constant, this will be K. Why I go for D? Because this is the distribution law. That's why this is D. So Kd will be product by reactant. So this will be S2 concentration divided by S1 concentration. So this parenthesis, this bracket, this is nothing but the concentration in terms of molarity, that is moles per liter. This is nothing but the molarity, that is moles per liter. So if I go for the expression Kd, it will be S2 by S1 concentration. So where Kd is also known as distribution coefficient or extraction coefficient, and it is independent of the total concentration of the solute and the phase volume. So it is independent, this is not dependent on the total concentration. So how much solute we have taken, this is not dependent on that. This will be dependent on how much solute is dissolved or distributed in solvent 1 as well as in solvent 2. So we have to place one equilibrium, that is the first solvent with the second solvent, and the equilibrium constant in terms of Kd, that is also known as distribution constant or extraction constant. Then what is S1 and S2? This is the concentration of solute in phase 1 and phase 2. So if I go for the phase 1 is aqueous and phase 2 is organic, then this will be solute in organic phase divided by solid in aqueous phase. If you imagine that total concentration to be increased until one phase is saturated and reaches the concentration SS1, the second phase will be simultaneously become a saturated one. If I go for a saturated, what is a saturated solution? Where maximum solute is dissolved in a particular solvent, that solution is known as saturated solution. There is no further solubility will be there. So that is known as a saturated solution, and which is less saturated or unsaturated solution, these are also known as sparingly soluble solutes. In sparingly soluble solutes, this is not 100% soluble, so this type of solutes will also be there. Then we have the thermodynamic partition coefficient, that is distribution coefficient, also defined in terms of K dash, that is K dash will be S2 by S1. This is the distribution coefficient. This is Y2 S2 by Y1 S1, or this is also S2 by S1 is Kd, and this Kd will also will be Y1 by Y2 into K dash, where S represents the activity of the solute and Y is the activity coefficient. It is activity where this activity coefficient is used, where the standard condition is not maintained. What is standard condition? Now in standard condition, the concentration of the solute in both aqueous and organic phase is considered to be 1 molar. But in other cases, that is in ordinary condition, except your standard condition, this coefficient is used, that is activity coefficient. This is for your condition except the saturated this standard condition. Okay. The variation in the distribution coefficient Kd can be seen due to variation in the activity coefficient in each of the phases. So when the condition changes, this activity coefficient changes, and accordingly the distribution coefficient will be changed. Thus you have to just remember that Kd is the distribution coefficient, which is equal to concentration of solute in second phase, that is the organic phase, divided by concentration of the solute is the aqueous phase, that is solvent number 1. Then for standard state, the concentration is taken to be or taken as 1 molar concentration, but at a concentration other than standard condition, this is the expression is changed to y2s2 by y1s1, this one, and y2 or y1, this is nothing but your activity coefficient. Okay, so the by using radio tracer, the concentration can be kept very low, and the distribution of the species in the two phases can be very accurately and conveniently quantified. Using radiochemical technique, it has been observed that the distribution coefficient of gallium chloride between ethyl ether and 6 molar hydrochloric acid. So that means this is the aqueous part and this is the organic part, like ethyl ether, and 6 molar hydrochloric acid 5%. And the concentration range is 10 to the minus 12 minus 2 into 10 to the minus 3 molar gallium chloride, and this will be the distribution will be accordingly. So this is just an example where the solute is gallium chloride and the two solvents are 6 molar hydrochloric acid and one is ethyl ether. Then another term will be there, that is known as distribution ratio. So what is the distribution ratio? This distribution ratio D is equal to total concentration of solute in organic phase divided by total concentration of solute in aqueous phase. This is a distribution solute. So the distribution solute, if I go for an example, if I go for benzoic acid, distribution of benzoic acid between benzene and water, that means benzoic acid is the solute, benzene is the organic phase, and water is the aqueous phase. Very simple. So here what happened, the benzoic acid, that is HBZ, that means the benzoic acid react with aqueous phase to give hydronium ion and benzoate ion, right? This is hydronium ion and benzoate. So what is the formula of your benzoic acid? That will be one phenyl ring which is connected to COOH, that is, or benzene connected to COOH. This is your benzoic acid. So benzoic acid react with water to give hydronium ion H3O plus benzoate ion. BZ minus means the benzoate ion. So in benzene phase, that is in the organic phase, what happened? This benzoic acid dimerizes. That means two molecules become one molecule, just like a polymer. This is dimerizes. Dimerizes to give a bigger molecule. So if I go for the distribution coefficient or the distribution ratio, then the three species, here we have three species. Number one is benzoic acid, number two is benzoate ion, number three is dimer of benzoic acid. Three species are here of solute, that is your benzoic acid, benzoate ion, and dimer of benzoic acid. Then what is what is distribution coefficient for benzoic acid? What is distribution coefficient for benzoic acid? It will be benzoic acid in organic phase divided by benzoic acid in aqueous phase. This is a distribution of benzoic acid in organic phase as well as in aqueous phase. So what is the distribution of benzoate ion? It will be again the benzoate ion in organic phase divided by benzoic ion in aqueous phase. Similarly, for dimer of benzoic acid, it will be dimer of benzoic acid in organic phase divided by dimer of benzoic acid in aqueous phase. Then the D will be total benzoic acid in aqueous phase divided by total, this is wrong, total benzoic acid in organic phase. This is organic phase divided by total benzoic acid in aqueous phase. So in organic phase, what are the, yes, right, in organic phase, what are the two components are in organic phase? We have benzoic acid as well as the dimer, and here it is written, that is benzoic acid and dimer in organic phase. Here O is written, it is mistakenly written here, it would be it should be organic phase. So in organic phase we have two components, that is in the reaction, the C here, in organic phase we have benzoic acid and dimer. So here also it is written benzoic acid and dimer. In aqueous phase we have benzoic acid and benzoate ion. So here it is benzoic acid and benzoate ion. So this will be the distribution ratio. That is, the benzoic acid is distributed as benzoic acid, benzoate ion, and dimer of benzoic acid. So inorganic phase we have benzoic acid and dimer. In aqueous phase we have benzoic acid and benzoate ion. Okay, and the last thing, it is evident that the distribution ratio will not remain constant over a range of experimental condition. Suppose we increase the pH of the aqueous phase, the distribution ratio will be lowered. This is because benzoic acid will be converted to benzoate ion, which doesn't extract in the organic phase. So as the pH will be down, that means acidic medium will be exit, and if exit medium will be more, then more and more more and more benzoate ion will be formed from benzoic acid. So this will disturb the ratio. Similarly, the distribution of osmium tetraoxide between carbon tetrachloride and water. So we have osmium tetraoxide is our solute, that is OSO4, and the two solvents are CCl4, that is carbon tetrachloride, and water. CCl4 will be the organic phase and water will be the aqueous phase. Similarly, the reactions will be, that is osmium tetraoxide exist as your dibasic acid, that is H2OSO5. This is a raw chemical, that is it is exists naturally, that is dibasic acid. So if I go for the different reactions, then this dibasic acid of osmium tetroxide will be splitted to H plus ion and HOSO5 minus. Then this will be again split to give H plus and OSO5 2 minus ion. And this is in aqueous phase. We have three reactions in aqueous phase. That the first one will be the dibasic acid formation, which is followed by the separation of first H plus ion or first one H plus ion. Then the second H plus ion will be again separated. In the organic phase, there should be a formation of a tetramer, which is OSO4 tetramer. So just see, in aqueous phase we have the components of OSO4, H2OSO5, HOSO5 minus, and OSO5 2 minus. So four components are here in aqueous phase. This is 1, 2, 3, and 4. In organic phase we have osmium tetroxide and the tetramer. So the distribution coefficient, distribution ratio will be D with the distribution ratio. So distribution ratio will be concentration in organic phase divided by concentration in aqueous phase. The concentration is in organic phase will be OSO4 and OSO44. So this is the one. And in aqueous phase we have four components. So these are the four components. These are all statistical methods. Okay. Then let's come to percentage extraction, that is out of 100. So distribution ratio is merely a concentration ratio, and the extent of extraction will therefore depend upon the volume of the ratio of organic and water phases. Since we are mainly interested in extraction, extent of extraction, we go for another practical term which is known as extraction percentage. So extraction percentage will be, that is if I go for And then total metal in the organic equilibrium will be 1 minus, if I go, F is the fraction of the metal in organic solvent, then 1 minus F will be the aqueous solvent. The total will be 1, that is 100%. If F fraction of the solvent or the metal is dissolved in organic phase, so what is left? It will be dissolved in aqueous phase. So 1 minus F will be in aqueous phase. So the distribution ratio will be total metal in organic phase divided by total metal in aqueous phase. It is symbolized as capital MO, capital MA. So for MO, I can write for organic solvent, it is F. That means it is for volume, it is F by V0. V0, no, it is not 0, this is O. So F by VO, the total volume of the solvent, divided by 1 minus F is the aqueous phase. So 1 minus F divided by VA, that is the volume of the aqueous phase. So by simplifying the terms or equation, we have F VA by 1 minus F V0. Just this is very simple derivation. And at last, we, by simplifying this, we at the end we will have F equal to dVO divided by VA plus dVO. F is the fraction of the solute dissolved. So if I go for 100 F, that is in percentage, it will be 100 D divided by D plus VA by VO. So now this is converted to your distribution ratio, that is percentage of distribution is converted to distribution ratio, that is 100D divided by D plus VA by V0, VO. Then percentage will be this one. Okay. So after this is the percentage extraction versus distribution ratio plot. This is just a relation, and we have separation factor. Another terminology is there, that is separation factor, that is component 1 in organic phase divided component 2 in organic phase divided by component 1 is aqueous phase divided component 2 in aqueous phase. That means here two components are there in two different phases. So by this is separation factor, which is used when two components are dissolved in two different solvents. So the reaction or the equation will be beta, which is nothing but your separation factor beta, which is equal to the C1O divided by C2O divided by C1A divided by C2A. That means here, if I simplifying these things, then C1O divided by C1A divided by C2O divided by C2A. So C1O, C2O, it is nothing but is distribution ratio of the first solute or first component divided by C2O divided by C2A. This is nothing but the distribution ratio of the second component. That means we will apply or we will use the separation factor beta when two components are dissolved in two different solvents. This is your separation factor beta. Just read all these things. I just touch all the parts in this unit. Then another factor comes, that is multiple extraction. It is simple where one short contact between two phases is made. The two phases are shaken until an equilibrium is attained. This is just same as your centrifuge, where the sample is shaken vigorously, that the two phases are in equilibrium. In this, one phase could be brought repeatedly in contact with fresh portion of the second phase. This situation would be applicable where one substance remained quantitatively in one phase while the other one was distributed in the two phases. Then in this case, one phase moves while in contact with the second phase, which remains stationary. So this is same as your centrifuge. So therefore, it is actually known as discontinuous counter current or pseudo counter current. That means one is move up having some with some current, and one will remain stationary. That is, it is treated as a pseudo current. So that means it is pseudo counter current. So this case a really counter current in which both phases move continuously in contact with each other in opposite direction. A true example of counter current is fractional distillation. Already explained. So multiple extraction with successive portions. So we have the derivation like this. If V1 ml of solution phase 1 containing W gram of solute in contact to equilibrium V2 ml of another solvent phase 2 immiscible with first, then C1 will be concentration will be weight by volume. The concentration in first phase will be W1 by V1, that is gram per milliliter, and similarly for C2 it is total weight divided minus the first one divided by V2 will be the second one. Then D will be phase 2 by phase 1. Phase 2 will be the weight, that is W minus W1 by V2 divided by W1 by V1. So at the end we have W1 equal to relation, that is W1 equal to W multiplied by V1 by dV2 plus V1. It will be your multiple extraction with successive portion. Then similarly from this equation we may deduce W2 also. So W2 will be here. Then after that, if I go for n number of components, then this reaction will be generalized, and this will be W2 becomes Wn equal to total weight. V1 is the volume in the first phase divided by D is the distribution ratio. V2 is the volume in the second phase plus volume in the first phase whole to the power n. If I go for, sorry, there is no n component, this is n times extraction. This is your expression, that is Wn equal to this much. Okay. Then the fraction remaining in first phase will be F1 Wn by W, and these things will be there. Just you read out these very simple things. Then classification of extraction system. There is basically in the following three steps, that is formation of an uncharged complex or extractable species, distribution of the extractable complex or the species, interaction of the complex or the species with organic phases. So three steps will be there. That is complex formation, distribution of the extracted complex, then interaction of the complex with the organic phase. The three steps are there. First is formation, second one is distribution, third one is interaction. Three phases will be there. Then with this background we will have different types of the extraction, that is distribution of simple molecule, extraction by compound formation, extraction by salvation, extraction by ion pair formation. So one by one we will discuss here. So distribution of simple molecule, that this involves the distribution of simple covalent molecule like germanium chloride, this is your mercuric bromide, and arsenic bromide between aqueous and inert organic solvent. Thus, this is simple molecule. The simple covalent molecule will be distributed between two phases, that is aqueous and organic phases, and accordingly their distribution coefficient, distribution ratio will be calculated. And another one, that is compound formation. If I go for a component extraction by compound formation method, then we will use some binding agents, also known as chelating agents or ester or some acids, to form a new type of compound or a complex compound which is separated and gets calculated accordingly. The reagent which fall under this category is known as liquid cation exchangers. where the component is extracted or the component is separated using different compounding methods. This is the component in terms of metal, that is Mn plus. This is the metal ion in aqueous phase, which is reacted with a compounding agent, or reagent, or a liquid cation exchanger Ha, which is formed a compound, that is Ma, with liberation of H plus ion. This is nothing but your complexing process or formation of a compound. The process is similar to solid liquid exchange, in which Ha is equivalent to an ion exchange resin. Okay, so we have three types, that is extraction by chelating agent. So chelating agent means it is just use of a chelating ligand. So in coordination chemistry, we all go through the ligand. So ligands are generally nothing but a group that can donate a pair of electron to the central metal atom or to its vacant orbitals to form a coordinate bond. That is donation from one end and acceptance from other end. That is donor acceptor concept. So in the ligands, in type of ligands, there are one type that is known as chelating agent or chelating ligand. Chelating means this is formation of a cyclic type structure. The very common chelating agents are ethylene diamine, or you may say ethylene diamine tetraacetate, that is EDTA ligand, which form a cyclic like structure through one ligand. So if I go for a cyclic like structure, this becomes this will attain an extraordinary stability. This will have an extraordinary stability, and this compound will generally extracted very easily, that it will be not reacted with anyone. And the next one is extraction by acidic organophosphorus ester. So organophosphorus esters may be used. It is followed by carboxylic acid and sulfonic acids, that is COH and SO3H. Okay, then chelating agents, this will have, just see here an example. Chelating agents, this contain a weak acid. Let us weak acid, we may say it is acetic acid, contain a donor group so as to form a bidentate chelate. Bidentate means donation from two sides. It is known as bidentate. And I already told to you that the EDTA, that is ethylene diamine tetraacetate, it is of hexadentate. That means it has 6 donation sites. EDTA, just see here. This is your EDTA. Just see here, this is EDTA. That is ethylene diamine tetraacetic acid. If I go for the removal of this 4H plus ion, this will be tetraacetate ion. And ethylene diamine tetraacetate is the chelating ligand, right? And here 6 donation sites are here. That just see here, 4 oxygens with 2 lone pairs. This is 1, 2, 3, 4, 5, 6, 7, 8. So out of these the carboxylate oxygen, that is C double bond O minus. So this is 1, this is 2, this is 3, and this is 4. So 4 donation sites with the 2 nitrogen. It also contain 2 lone pair of electron, because nitrogen has 5 valence electron, and out of 5, 3 valence electron make bond here and 2 electrons is remaining. And this 2 electron is 1 pair, so 2 nitrogen can donate 2 pair. So 4 oxygen and 2 nitrogen. So EDTA is an hexadentate ligand. Okay, so by using that ligand also, we can form, we can synthesize a chelating compound, which is very much useful to us to separate the component from a mixture. So other examples are also here, and this is also known as masking agent. Okay, it will mask. Then organophosphorus compound, in the similar manner, the metal atom reacts with organophosphorus to give a compound and liberation of H plus ion. So different, here is a, here there is a table here, I think. Just wait. One table is there. Where is the table? Extraction by solvent. Yes, this one. Or organophosphorus. Just see here. This is the structure of phosphorus. And this is the ester we will use. And these are the examples. So by using these things, we can separate the different components in a mixture. Okay. Then we have, after organophosphorus, we have the carboxylic acid and sulfonic acid. So carboxylic acid is generally C double bond OH and sulfonic acid is SO3H. So by using, but you just remember some example, and the effect of pH, effect of temperature, what are the different type of functional groups are reacted to give the compound, and it will be helpful to us for its separation. That is the main thing. Okay. And in your Versatic 9, okay, this is the percentage of recovery of the component, and this is another component. Then we have naphthalenic acid will be there, which is to a group of cyclic aliphatic monocarboxylic acid having the following general formula is here. Just read all these things and try to remember the examples, only the examples, nothing more, nothing more. And here the carboxylic acid reaction is here, and here on the basis of pH, how the naphthalenic acid reacts with metal with increase in pH. The order is iron, it is followed by copper, indium, cobalt, iron, manganese. So it is ferric and it is ferrous when pH change from 1 to 10. So after this we have extraction by solvation method. One solvent is used based on the solvation of the neutral inorganic molecule or complexes by electron donor containing extracts. The simple examples are cerium nitrate, ether, nitric acid, TBP, that is, and VO2NO3. These things are there. Then reagent containing oxygen bonded to carbon, such as ether, ester, alcohol, and ketone. Reagent containing oxygen and sulfur bonded to phosphorus. Example, alkyl phosphates and alkyl thiophosphates. Just under this category, you will only remember some examples which will be helpful to you in your exam, upcoming exam. Extract containing carbon oxygen bond. So carbon oxygen bond means it may be ether, ketone, alcohol. These things are there. And electrodonating reagents, but alcohol being amphoteric, that is both acidic and basic behavior will be there. So exist both donor and acceptor property. Then the function of the salting out of agent is considered to be threefold as given below. That is salting out of agents. That means salting means it is a compounding. That the component is converted to a salt. That means a complex salt. So providing a higher concentration of complexing anion, which by the law of mass action, which would increase the concentration of the complex and thus improve the extraction. It is followed by water will bind to the ion of salting out agent and thus become unavailable as a free solvent to compete with the organic phase for partitioning. So the water present in the medium will react with the component to form the salt or the compound. That's why the percentage of the water in the medium will be less, and it will be not compete with the organic phase for your partitioning. The addition of salt will lower the dielectric constant of the aqueous phase. This will generally happen because if the water gets reacted with the component or gets solvated with the component, then the dielectric constant automatically decreased. This is already covered up, that is a phosphorus oxygen bond. Then these things will be there, and you have to just remember some example, nothing more. Okay, so extraction by ion pair. Again the different examples are R3NH plus FeCl4 minus. These things will be there, and how this triamine or trialkylamine will converted to a salt, and that salt will change to different ions, and these ions will be separated based on their migration, that is speed or the rate of process. So these things will be there, and in ion exchange process, the order of preference in organic amine of different anions will be chloride will be migrated very fast, then nitrate, followed by your bisulfate and fluoride. So after this, we have another big molecule that is known as crown ethers. This is just a host molecule, and uh, these type of molecules have some internal space are there, in which outer molecules may be imbibed to form a host guest molecule type, and these crown ethers generally contain oxygen, uh, nitrogen and sulfur as the donor atoms. Examples are there or not? Just see the examples of crown ether. Crown ether. Just see, this is known as the crown ether. Yes, this one. This is 15 crown 5, 18 crown 6. That means here total number of atom is 15, and out of 15, 5 oxygens are here. So that's why the name is 15 crown 5. Similarly here, 18 number of atoms are here including oxygen, and 6 oxygens are here. So this is known as 18 crown 6. So this type of molecules are used for the complexion of the component present in different mixtures. So then the last part will be diluent and modifiers. So diluent means it is the suitable solvent in which the component is dissolved, known as diluent. It is the suitable solvent in which the solvent is the solute or the component is dissolved. It is known as the diluent. So the different properties of the diluent are they are mainly used to decrease the viscosity. Generally, the extracts used for commercial solvent extraction process are viscous liquid, and they cannot be used as such. Depending upon the metal to be loaded, an appropriate concentration of the extract is to be used. Thus, the diluent provides the solvent for preparing the solution of the extract of the desired concentration. Another role of the diluent is to decrease the emulsion formation tendency. A number of extract are surface active agent, and at high concentration tends to emulsify, specifically high agitation. The diluent improves the dispersion and coalescence property of the solvent. These are two very important aspects of the solvent extraction process. Okay, just these are the some characteristics, properties of the diluent. Then it is followed by your modifier. So modifier means one of the very serious problem in solvent extraction is formation of third phase, that is 2 organic phase. Most of the available evidence on the third phase formation suggests that it is essentially a solubility problem. If the solubility problem is there, then a modifier is generally used to overcome this problem. That is the third component. Addition of the third component, that is known as a modifier. If any byproducts are formed in the process of a particular solvent, then a third component is used, which is known as the modifier. The examples are isodecanol, 2-ethyl hexanol, p-nonyl phenol, and TBP. Then this is the order. The formation of the third phase is temperature dependent. Usually increase in temperature result in the disappearance of the third phase. The appearance of the third phase is more common with aliphatic diluent. Very important. If I go for the aliphatic diluent, aliphatic means straight chain diluent, not benzene type. It is straight chain, not cyclic. It is straight. In the case of high molecular weight amine strength, the tendency for third phase formation with different anion follow the order nitrate, chloride, and sulfate. These things will be there. Then at last, we have the summary part that we have discussed in this unit 2. We have discussed the distribution law given by Nernst distribution law, that is distribution coefficient is there, distribution ratio is there, then which is followed by your separation factor. Then we have some complexing agents like chelating agent, carboxylic acid, organophosphorus. These things are there. And at the end, we have a short discussion on diluent and modifiers. So in this unit, you have to remember only the examples under each category, and you have to write few lines on the particular mechanism or the method. So for today, this much discussion will be possible, and tomorrow we will have the next 2 units. And if anyone have any question or any query, we will have maximum 5 minutes for discussion, then we may wind up. Okay. Actually, students, in your IGNOU study material, many things are there. So it is not possible to cover all the things within 1 hour. It is very difficult. So intentionally, I skip many things which which will not come in your exam. I just highlighted or point out the mathematical expressions with the mechanism, examples, and the things which are required for your examination point of view. And if you go for the details, you may follow your study material. And in these 7 days, at the end of the day, that is at the last day, on the last day, we will discuss the overall discussion we have made in our paper 2. So if no questions are there, we may wind up the session. So thank you to all for your patience hearing, and tomorrow the same time, same platform, we will meet again. So thank you to all.
Thank you, sir.
And also one thing, um, one from you, from your group, may create a WhatsApp group. It will be helpful to you all to communicate or to share information, material, any examination related things. It will be helpful to you all. So one may lead and collect all the numbers, the WhatsApp number, and he or she will create a WhatsApp group, which this is non-official. This is non-official WhatsApp group. So it is for you only. So you can share your information or anything else in that group. Okay. So if any examination related or practical or theory related informations will come to me, I will intimate you in our future theory classes. So thank you students.
हेलो हेलो
सर तो गए।